All right, so now we're going to learn about some additional methods to prepare alcohols. The first is actually more reduction type methods, but starting with even further oxidized compounds, right? So we're now starting with, instead of just being a ketone or an aldehyde, we're starting with a carboxylic acid or an ester. So here we can use lithium aluminum hydride, and they will reduce a carboxylic acid or an ester all the way to an alcohol. Notice that sodium borohydride we can't use here, right? So lithium aluminum hydride is considered to be a stronger reducing agent than sodium borohydride. Both work fine for ketones and aldehydes, but if we have a carboxylic acid or an ester, it has to be the lithium aluminum hydride. And so these will reduce, again, all the way to an alcohol. So turning this carboxylic acid group or this ester group, you might want to go back and watch that functional groups lecture from, I don't even remember what chapter, 1, 2, or 3, can't remember, probably 2, I don't know. Anyways, in terms of remembering what an ester is, these are molecules that have this key pattern here. Carbonyl group directly attached to an oxygen, and then there's something else going on, some other carbon going on the other side of that. Okay, I guess that's fine. And these will always yield primary alcohols, note. So we can see the mechanism for these. It's actually quite interesting, very similar to before. So what do you think when you hear hydride? You think a hydrogen that's playing the role of a nucleophile, right? So same thing here. First step is we have our nucleophilic hydride hydrogen attacking the electrophilic carbonyl carbon. And then, oh, hold up, killing a fly. There we go. All right. And then that carbon can't have more than 5 bonds, so that pair of electrons is going to jump up onto that oxygen. So then here, remember before I was saying this pair of electrons would love to come back down, but it can't because there's no leaving group. Well, in this case, when we have an alcohol, or I'm sorry, an ester or carboxylic acid, there is a good leaving group, and that's this right here. Honestly, it's not a great leaving group, but it's good enough that it can be kicked off. So the next step here is this pair of electrons comes back down, reforming that carbonyl bond, that carbon-oxygen double bond, and kicking off that leaving group here. And so notice that one of the byproducts of this particular reaction would be methanol, right? So this guy gets kicked off. It's really this methoxide ion, but it'll be protonated later. All right, so first step again, sorry, just to go back, it's the nucleophilic attack. We have our nucleophile being that hydride hydrogen, and then loss of a leaving group. So now we have kicked off that alkoxide group right there. And now we've arrived at just an aldehyde, right? But we know that aldehydes also will react with aluminum hydride. So that's why we have this second round of reduction here, where it attacks, that pair of electrons jumps up. So again, we have nucleophilic attack of that nucleophilic hydride hydrogen. And then lastly, now we get here, and again, this guy would love to come back down, but there's just no good leaving groups. So it's kind of stuck, and it's waiting to be protonated from, in this case, water or any protic solvent would do. All right, so when you treat a carboxylic acid group or an ester with aluminum hydride, there's 2 rounds of reduction at first. First, it reduces to an aldehyde, but it's not going to stop there. It's going to go a second round of reduction all the way to an alcohol. And again, because you started with an ester or a carboxylic acid and there's 2 rounds of reduction, you're always going to get a primary alcohol at the end. All right, so now we have one last method of preparing alcohols, and this is actually a really important one. This is using what's called a Grignard reagent. And I know it's spelled Grignard, but it's pronounced Grignard. And so what happens? So what is a Grignard reagent? So it turns out that if you take an alkyl halide, I don't know why they do it like a generic alkyl halide. It's literally always going to be a bromide. And you mix in solid magnesium metal, that magnesium atom will actually bury itself between the carbon and the halogen bond. So it inserts itself in the middle here. So we would actually, our Grignard reagent looks something like this, right? So, and you can, usually there are restrictions in terms of it has to be sp3 hybridized, blah, 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 blah. When it comes to a Grignard, it can be literally any halogen that you use. So in whether it's this phenyl group on the on your alkyl halide, or this would actually be called an aryl halide, but don't worry about that. Bottom line is this R can be anything. There's not really any restrictions on there. As long as there's that halogen bond, magnesium can insert itself. Okay, so again, whether it's a big old benzene ring or just a normal old alkane chain, it really doesn't matter. So Grignard reagents are really, really useful. Let's see why that is for right now. So the real thing here, the key thing to remember is that magnesium, being a metal, has a ridiculously low electronegativity value, even compared to carbon, which we don't really think of as an electronegative atom, but in comparison to these group 1 and group 2 metals, it is. So that means that this bond right here has a partial negative charge on the carbon and a partial positive charge on that magnesium. And this difference is quite enormous in terms of the electronegativity. So really, one way to think about it is to think about this bond as being actually an ionic bond, where you have a carbon ion being ionically bonded to the magnesium. Okay, and what do we know about carbon ions? These guys here are great nucleophiles, right? So a Grignard reagent, when you create a Grignard reagent, you create a really nucleophilic carbon. Okay, so these can react with aldehydes and ketones, much like we saw before with our hydride reactions. Okay, here what we're going to have is instead this R group. This is actually really what we should do, is it's like BRMG, right? And it's this bond right here. You can think about it as a carbon ion, but really you want to do it like using your Grignard, right? So it's this bond here is reaching up and attacking that electrophilic carbonyl carbon. And again, what's got to happen? Carbon can't have more than 5 bonds, so that's going to jump that pair of electrons up onto that oxygen. So the first step here is you have nucleophilic attack, where that Grignard reagent, and in particular the carbon in that Grignard, is going to be the nucleophile attacking that electrophilic carbonyl carbon. And what happens when we get here? Well, again, this pair of electrons would love to come down, but there's no good leaving group to kick off. So instead, it's got to wait until you follow it up with some sort of protic solvent, and you get a proton transfer that will then create that alcohol group. Okay, so very similar to what we saw before. What's the big difference? We have a new carbon-carbon bond that's formed, right? So we've only seen one other method of generating new carbon-carbon bonds, and that's using terminal alkynes. So Grignard reagents is a way of creating yet another carbon-carbon bond. Okay, and again, this sort of cool thing about Grignard, or the really powerful thing, is that this R can be absolutely anything you wanted. Okay, so big takeaway here is that Grignards will react with carbonyl carbons, or whether it be a ketone or an aldehyde, to create an alcohol, as well as that new carbon-carbon bond that's formed. The one thing about Grignards that is kind of a pain in the butt to work with is they cannot be used with any sort of a protic solvent, because Grignards are not only great nucleophiles, but they're also really strong bases. This is a big consideration when you're doing chemistry in the lab. You want to make sure that you've dried your glassware, because any sort of water that's coated on the inside of the glassware will react with that Grignard. And so what happens, again, because it's just a really strong base, is if there's water in there, it will just protonate itself with the hydrogen from the water molecule. And the reason why this is so kind of a bummer when it happens when you're not expecting it, is you've sort of taken all this time to create your Grignard reagent from your alkyl halide. And what are you going to get if you have water in there? Well, it's just going to be replaced with a hydrogen. So you're just going to create an alkane. And this, we know, is really unreactive, right? So in a way, it's kind of like a dead end that you've gotten yourself trapped in. So you just have to make sure that when you're using your Grignards, you don't have any source of acidic proton around. Okay, so Grignards, again, we can use them with either aldehydes or ketones in order to create. So this first example here is using a ketone. It's just a methyl group on our Grignard. So we've created an alcohol, but also with that methyl group, that new carbon-carbon bond that's been formed. If we use an aldehyde, that's also will undergo one round of Grignard addition, where we've created a new carbon-carbon double bond as well as our alcohol group. But if we use it with something more highly oxidized, so an ester, for example, it will undergo 2 rounds of Grignard addition, just like we saw with the lithium aluminum hydride. So instead of just having 1 round, it will create 2 new carbon-carbon bonds as well as an alcohol group. And so your discussion for this will be to go through and draw the reaction mechanism for those 2 rounds of addition. Again, one of the key components is that you have a decent leaving group with this portion of the ester molecule. I will note that if we started out with something like a carboxylic acid, and then we tried to use a Grignard, we would not get any product. Why would that be? Well, remember, Grignard is both a strong nucleophile, but it's also a strong base. So what would end up happening, well, I guess you wouldn't get nothing. You would get a deprotonated carboxylic acid. And in this case, if you used CH3 MgBr, you would get just ethane back, right? So you can't have a carboxylic acid in the presence of a Grignard, because the Grignard's just going to steal that acidic proton. All right, so now just to do our little review. So the first thing we got to worry about is mechanism. So we had 2 new reduction techniques. So these were these reduction techniques, both of which you should know the mechanism for. Okay, that's just when you have lithium aluminum hydride, meaning that you have that nucleophilic hydrogen, as well as our Grignard. I want you guys to know the reaction mechanisms for the Grignards as well, being reacted with either aldehydes, ketones, or esters. Remember, Grignards don't react with carboxylic acids. Good news in terms of regioselectivity. There's nothing you got to worry about here. It's pretty straightforward. You're always going to get substitution on that carbonyl carbon. Same with stereoselectivity. There's no considerations for any of these reactions also. So you do have to know the mechanism. You obviously always have to know what the products would be. And you do have to know the mechanisms for these, but they're all very, very similar. No regioselectivity, no stereoselectivity.